Hey everyone, so today we're going to go straight into Euler's methods, which is part of your differential equation chapter in your textbook. Let's get straight into it. When do we use Euler's method? So you use Euler's method when you're given a differential equation. Obviously, we're doing a differential equation chapter. Let's just say dy dx equals x squared, and you're asked to solve for the y value when x equals to some value, so x equals to 1. And of course, you're given a point. Generally, what Euler's method does is it skips the integration process. If you were to do this normally, you would integrate. So dy dx equals x squared, you would integrate to solve for y in terms of x, and you get that plus c. That's when you use your 0, 0 to solve for it, and then sub in x equals 1 to get your y value. But Euler's method skips all that. It actually gives an estimate of the y value without doing any integration at all. So why is that so useful? So the reason why it's so useful is if I gave you a differential equation where it was impossible to integrate, for example, dy dx equals x squared plus y squared, you can't integrate that in this course. So what you actually can do is use Euler's method to still find that y value without knowing how to anti-differentiate this whole equation right here. So that's why we use Euler's method. Let's see how it works. So how does Euler's methods work? Well, funnily enough, the foundation actually comes from the simplest gradient formula you should know, which in this case is the y2 minus y1 over x2 minus x1. I'll draw a graph so that you can see this. We're going to write it in a different notation. So let's just say we have our x coordinates. Let's put it right there. If you have an x, you want to find the y value, it will be fx. And if you have x plus h, which is your y2, we want to get our y2 value, right? Then it will be fx plus h to get your y value. Okay, so in function notation, this formula is written this way. If you want to find the gradient, f dash x, that's the gradient. Then you have y2 being fx plus h, minus y1, which is fx right here. And of course, you divide that, x2 minus x1, x2 is x plus h, minus x1, which is x, so minus x. And you simplify this, and what you actually get is pretty much your first principle. You should have learned this in method, or you would learn it soon, divided by h, because the x cancels out. So what Euler's method does is it takes this into a new level. What we do is, remember, the goal of Euler's method is you're given a differential equation, we just say x squared plus y squared, and the purpose is to find a y value when x equals, let's just say 1, given that you know x equals 0, y equals to 0, for example. So what actually happens is you're actually trying to find this value right here. That's your next y value, let's say. And you're given a starting point, 0, 0, that would be your fx value, which is at y, and then your x value will be 0, which we'll need later on when we do an example. Okay. So if you want to find the fx plus h, then we're just going to manipulate our equation around h, bring it up here, times it by f dash x, and you can bring the fx to the other side as well, so that's plus fx. And what you actually have is your original formula, your Euler's methods formula. Fx, so to get your new y value, it's actually the step size, h, which is the difference between your x value and your next point, times by your gradient function, f dash x, and plus fx, which is the old y value. So that's the Euler's method. It's actually quite ingenious. And yep, that's pretty much it about Euler's methods, guys. Make sure you just know this formula and you're all set. Do some of your textbook questions as well. And if you're still struggling, just leave me a comment and I'll do a tutorial video on Euler's method. But it shouldn't be too much of a problem. Just know your formula and know how it works. Should be fine. Cool, and that's pretty much it for today, guys. Thanks for watching.